Hello everybody, welcome to Cranky Calculus. We're going to talk about concavity today, which deals with the second derivative and anything to do with the second derivative, such as inflection points as well. So let's get right into it by learning what the heck concavity is first. So just seeing a drawing here, we have a function is concave up that looks like anything that looks like a U. So this is going to be concave up. This is when our rate of change is increasing. A feature that we can do to determine if something's concave up or not, if we're just a little unsure, if you're to connect any 2 points which make a secant line, if the secant line is above the graph, then we're going to be concave up. So again, any 2 points here, secant line, all these secant lines I'm drawing are above the graph, we're going to be concave up. Likewise, something that's concave down. It's concave down looks like a frown. So this is concave down. All right, that means the ROC is decreasing. So our rate of change as we go is getting smaller and smaller and smaller. Same idea with the secants. These secants are going to be below the graph, and that's how you can graphically tell if we are concave up or concave down. You can even look at this graph right over here to the right. If I can zoom out far enough, there we go. This graph to the right, you can tell that it does change concavity. About right here-ish. If we're just looking at a graph, it's kind of hard to tell. And everything left of that point I did right there is concave down. Everything right of that is going to be concave up. When we do change concavity, that's called a point of inflection. So we got to look at our concavity test here. If f double prime is greater than 0, we're going to be concave up. If f double prime is less than 0, we're going to be concave down. Inflection point, again, is only when we change concavity. Lots of people make errors and they think that that means that when the second derivative is equal to 0. That doesn't tell us anything. We only care about it when we change concavity. Right into our first problem here, we have f of x is going to be this polynomial. Find the intervals in which f is concave up, concave down, and we're also going to find the inflection point. So the first thing we're going to do here is find the first derivative. And this is just simple power rule as we go through. And I don't care about the first derivative, so I'm going to use it, though, to springboard me to find my second derivative, which is going to give me 12x squared minus 12. I'm going to take out a GCF of 12. And factor this as much as I can. This should be some fairly simple Algebra 1 work after the derivatives here. And we're going to get this to equal 0 at plus and minus 1. Those are potential points of inflection. They're not inflection points yet until I determine that concavity does change. So I'm going to make a sign chart here of f double prime. I'm going to plot these points on there. And since this is an upward parabola, our right end behavior is going to be positive on my sign chart, and we're going to change signs at 1 and negative 1. So you can tell here where we do have a change in concavity, and you can tell here when we're concave up and down. So we are going to be concave up on the intervals from negative infinity to negative 1 and 1 to infinity. That is because f double prime is positive. And we're going to be concave down on just the interval from negative 1 to 1 because f double prime is negative. And that's all you need to do to justify everything here. Okay. As we get to the inflection point, we actually do have 2 inflection points. And these are points, so I need to state out not just the x values, but the y values as well. Clearly tell that we are changing concavity here at negative 1 and 1. So I do want to find those y values. So f of negative 1, if I substitute in a negative 1, I'm going to get negative 1 to the 4. Minus 6 times negative 1 squared. That's going to give me 1 minus 6, which is negative 5. So I have a point of inflection at negative 1, negative 5. And if I plug in a 1 into that, I'm going to get 1 to the 4th minus 6 times 1 squared. I just get another negative 5. So I have a point of inflection at negative 1, 5, and 1, 5, because f double prime changes signs. All right, that's going to wrap up our first problem here, and let's go ahead and move on to the next one. This problem, we are given g prime, so let g prime be that polynomial function, find the intervals in which we're concave up and down, and find all inflection points. I'm going to say just the x values. So find all x values because we can't find the actual values because we don't have g. So find all the x values. And we're going to go ahead and justify our answer. So since I have the derivative here, I need to take the second derivative. This is going to require product rule. So we're going to end up with the derivative of the first here is going to be a little bit of chain. So it's 3x plus 1 all squared, x minus 4, plus leave the first. And the derivative of the second is actually just going to be 1, so times 1. I'm going to set this equal to 0. Instead of expanding everything and making this all messy and then condensing, we can actually find a GCF right here. I'm going to take out a GCF of x plus 1 all squared. That's going to leave me with a 3 and x minus 4 and an x plus 1. All in that big old parentheses. I have too many parentheses. Okay? Much easier than expanding is to find the GCF. So I'm going to get x plus 1 all squared, and this is going to give me 3x minus 12 plus x plus 1. So that second parentheses here does simplify kind of sort of nicely. I'm going to end up with 4x minus 11. So I'm going to get potential critical points of x equals negative 1 and x equals 11/4. So I'm going to go ahead and make my sign chart here for g double prime. I'm going to get negative 1 here. I'm going to get 11/4 over here. My right end behavior, since all my x's are positive, I'm going to be positive. At the 4x minus 11 factor, I have a power of 1, so I do change signs. But at negative 1, I do not change signs, because that's going to bounce off the x-axis. So with the sign chart, we can determine what our concavity is. So I'm going to be concave up on 11/4 to infinity, because f double prime is positive. We're going to be concave down on negative infinity to negative 1. Don't include negative 1, by the way, because that's not what our test for concavity tells us. And this is because f double prime is negative. We have actually just one inflection point. We have one inflection point. Since we don't know the y value, I'm just going to say at the x value at x equals 11/4, because concavity, or because actually I'm going to do this, because f double prime changes signs. I didn't even finish the word inflection. There we go. So that is going to wrap up that question right there. And I do not have an inflection point, by the way, at negative 1, because we do not change signs. So it's a huge mistake that a lot of people make, is you have to know that you only have inflection points when concavity changes, not when the second derivative is equal to 0. Do our last example here to wrap up this set of notes. To the right is the graph of h prime where x is greater than or equal to 0. Where is h of x concave up, concave down, and justify? So this is h prime. So since this is a graph of h prime, if concavity represents the rate of change, whether it's increasing or decreasing, this h prime is the rate of change. So when is the rate of change increasing? So concave up is when h prime is increasing. When is h prime increasing? It's actually increasing from this blue dot right here all the way up, it looks like, as we go through. So we're going to be concave up on 1 to infinity, because h prime is increasing. And we can say the same thing for concave down, but obviously the complete opposite. So concave down here is when h prime is decreasing. So we are concave down on, we'll include 0 because it's included in our interval here, from 0 to 1, because h prime is decreasing. And this is going to wrap up our video here for concavity. Please like and subscribe for more videos like this.